Okay, yeah, so thank you, and I would like to thank the organizers for the invitation. Yeah, I'm again going to talk about squares, unfortunately. I just try to avoid the topic, but it somehow always come back. So, yeah, yeah, and this was really, so, okay. So what I want to talk about is just something we did. So this is joined with Nam. And this is really an addition to this older paper. PFA and guessing house, right? I think it was around 2010. And yeah, so this has several results there, but the technical result is really about squares, and then he applies these squares to the getting strength of PFA and some this guessing house. And, yeah. Okay. So what kind of squares are used there? And maybe also there is another connection of this to a paper which is four authors' papers, Jensen-Schimmerling. Jensen-Schimmerling-Schindler-Steel. And this is called stacking mice. And yeah, and there they also, yeah, so they use this method of stacks to build a KC model and prove some covering properties which allow to derive strength from the consistent strength for the failure of square. So what are the exact statements? I will write that, but so let me say, so we were trying somehow kind of believed, so this uses the KC model, yeah. It's a ZFC construction. This Nam's paper uses the core model induction method. So it's believed that that's a universal method. So we try to, so when you do this, then you have to, the problem is always to get the results for small cardinals. So this, when you do this, then you are somehow further away from very small cardinals. When you use this method, it's easier to get results about the small cardinals. So let me write down. Okay, so let me recall what is a coherent sequence. Of clubs, if and only if alpha bar is the limit point of C alpha, then yeah, yeah. So these are clubs, yeah, and coherency means that if alpha bar is a limit of C alpha, then C of alpha bar is C alpha intersection alpha bar. And that's one thing. And the other thing is that C subset of lambda is a thread through such a sequence, and only if, well, so briefly written is that if I add C to the at the end, I still get a coherent sequence. Yeah, so C alpha. So it behaves. So yeah, so a coherent sequence means that every next set is just thread through the previous one. And then a coherent sequence is a square lambda sequence if and only if. So sequence of length lambda would be a square in parentheses lambda sequence if and only if it does not have a thread. And square sum lambda. So this is a sequence of length lambda. This is a sequence of length lambda plus, if and only if it has length lambda plus and type of each C alpha is at most lambda. So, and it's an old fact is that where lambda sequence is a square lambda plus sequence. So that's the so yeah. So when we are looking, yeah. So we know that if this fails, that's has some kind of strength, and it's harder to construct this than that. Yeah. If we look at the single cardinal, say at the, so we are going to talk about small regular cardinals. Yeah, the situation at single cardinals is different, and I will not talk about that. But at the regulars, yeah, yeah. If we look just a single failure, that's very weak. A failure of this thing would be Marlow. Failure of this, yeah, failure of square is Marlow, and failure of square of this thing is weakly compact. Yeah, but so yeah, so people got interested in this because when looking at successive failures, because that's, for example, something which follows from forcing axioms. So that gives one way of establishing strength for forcing axioms. And then even for successive two, this consistency strength just jumps up quite dramatically. And yeah, and so this is what these two papers are about then, yeah, among other things. And but let me just say one thing. Yeah, so this is kind of pi 1 1. because you just say there does not exist a square sequence. But the non-existence of threads is guaranteed by this. While this thing, I want to. Yeah, so this is one means that we talk about subsets of lambda plus. Yeah? Because you have to say that every sequence is threadable, but you don't. There is no concrete way how to get these threads. So it suggests that this may be kind of, if you want to fail this, it may be kind of stronger. And yeah, and so the theorems were, so it was something like this. So assume, so kappa is at least omega 3 and plus kappa is threadable plus well first at kappa, yeah. Then there is a sharp for an inner model with proper class of wooden cardinals. Looks proper class. Do I need some, now I'm not sure if I need some cardinal arithmetic here. And then there is Strang's paper. Yeah, assume. Yeah, I'm all cardinals I'm talking about are regular. So kappa to the omega is kappa. Kappa is at least omega 3. And yeah, actually, yeah, let me make it easier. And let me also assume kappa 2 to the kappa is kappa plus. Yeah, the theorem is more general, but let's just do this. And okay, so the difference is that there is threadability here and there is failure of square here. So this appears to be kind of weaker hypothesis. Then but the conclusion is stronger. There is this. Yeah, and then we collapse then in if G is generic collapse of, and we collapse kappa to omega. And we look at in VG, there is a proper class model. There is a model, this proper class model. Such that it has all reals and satisfies the ADR plus theta is regular. Okay. So this makes the conclusion stronger. This thing is in the region of wooden cardinals, which is a limit. Okay, so, but yeah, but the hypothesis appears to be stronger. So, yeah, and because of this other fact, so one may wonder, yeah, so whether, yeah, so it's, I agree that this is probably a somewhat narrow question, but it is of some interest. I think that whether this theory is really weaker than this theory. Okay, so I think we don't know, but we can improve. So what I want to say is that we can improve this theorem by weakening the second part of the hypothesis by taking not square. And actually, yeah, I didn't, yeah, okay, so I should say, I didn't say what kappa is here. Kappa is, so we can make smaller kappa. So kappa is kappa at least omega 1. Yeah? So, sorry, omega 2. So we can, this is probably the smallest you can have because omega 1 is non-threadable. And let me say also that, yeah, so let me just write the theorem. So the above theorem holds, can be can be strengthened by replacing. And okay, so this is probably the best I am aware of what one can get, but I would like to mention one thing, that this is actually not that far from the known upper bound. So I think there is also Larson, right? Let me just write it in a vague way. The upper bound for the hypothesis above is somewhat below this wooden limit of wooden cardinals. So that's, yeah. So it looks like it's getting close. Yeah, so let me, yeah, I don't want to do too long, but what I want to say about this is that most of the argument actually is in Nam's paper already. So when one look at that paper, there is exactly one spot in that paper which needs a revision. Yeah, and so I probably say a little bit about that one spot, and the rest can be just transferred either verbatim or with some obvious modifications. Yes. Yeah. Kappa can be all of 2 here. Yeah. Yeah, but there the hypothesis was kind of quite, I would say, overstretched. Yeah. Yeah. So there are, yeah, so it doesn't entirely match. Yeah. And I think also these hypotheses which were used there were probably stronger than this. Okay, so let me, okay. So let me just split this into 3 steps. Yeah, so the step one one constructs. Okay, so let me, yeah, so maybe let me say this also, that so in this kind of arguments, this, so one really proves constructs model of AD plus, and then uses a theorem which is, I believe, due to Martin and Woodin. So that the models of AD are precisely those where the Solovay sequence, where theta is a limit of the Solovay sequence. Yeah, so. actually, yeah, so what we are using, what is used here is the from right to left, and that's actually the hard part. I mean, the from left to right, it's actually an old thing. I think it was known to Soloway, and it's not very hard to see. So really what one does is one wants to construct a model of AD plus and show that theta is a limit of theta. And so, yeah, so step one, so one constructs, so this is, yeah, so one works in this generic extension where one collapses kappa, yeah, and one looks at the lower part model over R. Okay, I mean, if you, yeah, okay, so it would be incorrect to write alpha, but if you don't know what LP is, then let's for the moment pretend that you are looking at L of R, because what I'm going to say will look very much like that. Yeah, just that in L of R, you cannot have a limit of that. Yeah, and yeah, and okay, and then you want to see, and then step two is you show that, yeah, you look at the height of this LPR, and you show that it must be strictly smaller than kappa plus. Yeah. And this is where this is one place where the square construction comes in. Yeah. So this is needed because the argument there, yeah, so there is some core model induction argument which uses lifting some operators and some other some inner model operators and some other things, and that argument is based on the fact that one can take small holes which are countably closed and cofinal in the height of this thing. So really the square is used to show that this thing has a small cofinality, this height of this thing has small cofinality. So the top part of the square is used, yeah, so not, this uses kappa or previously. And then you show that I am again off. Yeah, okay. Yeah, thanks. Yeah. Yeah, so the top part is, let's see. So I'm at omega 2. Aha, I see. Okay, you know. Yeah, so actually, so I can assume kappa to the less than omega. That, so the assumption kappa to the omega equal kappa is actually a bit, I can weaken it, right? I can assume it for the predecessors of kappa. I'm thinking of 2 to the kappa. In your hypothesis. Mm-hmm. I wanted to get it to the situation. I really wanted to get the smallest possible thing. So I wanted omega 2 threadable and square sub omega 3 fails. So it square sub omega 2 fails. So for that, I need to assume CH. So, so, so if I write this, that would, okay. Yeah, okay. I mean, I just wanted to make it connect many things, and that probably is, yeah. Yeah, so here you have this and this. So maybe I should write down the statement then. Okay. So let me just write exactly what. Yeah, so what I wanted, so the smallest possible situation is this. Yeah. Yeah. Yeah, I want it because this is something which you don't get from these other arguments, right? So you get to the very bottom where this makes sense at all. Value of squared kappa. So this is a sequence of length kappa plus. So this would be like threadability. This would give you threadability. So this is omega. No, I'm still. Yeah, you're right. So I need. Yeah, I think that's the thing. Yeah, so omega 2 is threadable and there is no square sequence at omega 3, right? Yeah. Okay. And then, yeah, and then you, okay, so this is kind of standard and it has been done in this kind of argument since ever, yeah? So then you just, you can pull this down to omega 2 and its threadability. Yeah, and so, yeah, and so my point is, yeah, so this, yeah, so really what you need to prove is this, yeah? Just, okay, now it is kappa plus, yeah, I'm sorry, yeah. Yeah. So what you need is to prove this, yeah, and then these other standard things will then tell you that the cofinality must be very small. So, and yeah, So what's the problem here? You know, you just try to run the usual construction of square, but in this model, yeah. And the problem is that you don't have uniform Skolem functions in a, well, you do have them in some weak way, but not. So you can. So basically, the in these models, the construction of a square sequence. So there are many ways how to organize it, but one way is that you just break it into two parts. Construct a coherent sequence. Let's just call them B alpha. So yeah, so assume this is not smaller but equal. Yeah, so then you can construct. You would construct such a sequence, and yeah, this is done. B alpha consists of critical points of maps. Yeah, so you look at collapse. You look at levels which project to reals. Yeah, so you can think of reals as of omega 1 or something like that. Yeah, so these are some, let me say sigma 0. There are some nice preserving maps. These are levels of the model which project to reals. The maps have some degree of preservation, but it's very weak. It's important that this is 0 here. Yeah. So at each level of definability, you would look at something like sigma 0. Yeah? And yeah, and this is actually the hard part in general. Yeah, because if you so you want that they have some other reasonable properties, but that alone give you a sequence which is not threadable. No, in most cases it will be non-threadable in any outer model unless you collapse things to omega. Yeah, this is okay. I don't take it as a theorem, but that's what happens often. Yeah, so in many situations this is actually this takes some work, although in this particular situation, when you talk about LP, is not that hard because it very much looks like in L. Yeah. And when you have that, yes. And when you have that, then part 2 thin out B alpha to get C alpha of short lengths. Yeah, so this would have done short lengths. So the thing is, when you are doing constructing this, you don't really need Skolem functions which are uniform in any strong way. So you can run. So you can run just the construction which is in choice models. You can run inside this model somehow, yeah? Because at some point you need to take countable holes, but all you need is DC. You don't need to somehow watch the things too carefully. Yeah? So this can be done, and so and if you are in choice models, this part is easy because it's just one algorithm which can be run in all kinds of situations. But that's hard in models where you don't have which are not self well ordered, or how to say it. Yeah? So in this particular situation, this is the hard part. Yeah? So let me just sketch what to do. So we are running the construction. Yeah, this goes in the generic extension after collapsing kappa to omega. So what we do? Yeah, so how to? So we need to get back to V, yeah, because we are assuming that square fails in V. So we run. So in this particular situation, we have, let's just work with concrete cardinals because I get confused. So we have omega 1. So this means that H omega 1 of Vg is just H omega 2 of V adjoint G. And so what we do is we run this so-called S construction. This is omega 2. Yeah, so we collapse omega 1. So omega 2 of V becomes omega 1 of. Yeah, so now I'm assuming CH. So, okay. Let's see, what did I, where did I write it? G, I said, let's see, aha. Yeah, because I'm mixing those two theorems and that was a bad idea. So work in the omega 1. Yeah, so. Yeah, okay, so you just do everything, you just collapse omega 1 here. Yeah, if you, yeah, you know, the problem is that you need countably closed hull. So if you work in this other context where 2 to the omega is omega 2, then you have to go one cardinal up. So. Okay. In VG, we have below omega 3, we have finally many levels of LP of R, which project to R. Yeah? So we run this construction, which is called S construction, and we get a similar kind of model in V. So LP in V, the same in V about LP. So this is one step. If you want to construct this sequence B alpha, you need cofinally many levels which project to reals. Okay, and now we need to thin them out. And Okay, and what one does here is, yeah, it's kind of obvious, but we didn't see it for a long time. Because, you know, what you want a square sequence in V. I mean, all of these constructions would, which you attempt to run, would give you a square sequence in LPR, which I doubt there is such a thing. But you know, what you want is really a square sequence is V. So run. So now, yeah. So we have a, because of CH, we can fix a well order in V, a well order of reals. So basically, or we can enumerate them, yeah, in omega 1. And now you can define, you kind of, you know, because the truth predicates for the levels of these are have uniform definition, which takes place inside LPR, or they are definable over these structures, yeah. So you can define something like Skolem function now using this enumeration. So those Skolem functions will be outside of LPR, but they will be in V. And you are not going to do any serious use with them. You are just going to use them to form certain countable halves. And because of there is enough preservation here, which guarantees that these halves are shifted correctly along, yeah. So this is, you have this, for each alpha, this B alpha consists of this alpha bars, and yeah, so there is some directed system of maps, and it just shifts those holes, yeah. So then define one using those define holes, countable holes the same way as in the original construction of C alpha. Yeah. And the point is, or maybe I should write this alpha bar alpha. The maps sigma alpha bar alpha shift these holes correctly. Yeah, and so that one can run the old construction. I'm out of time anyway, so I'm not going to write that, but whoever is interested can look it up. Yeah, it's pretty straightforward. So yeah, so it's, yeah, so really I don't know. We didn't see it because yeah, so the point was that you get a sequence which is inside your model V you start from. Yeah, although you just combine, you need these B sequences to guide your maps, and but you do the thinning from outside. Yeah, so this gives V. Yeah, but then it can apply to that. Yeah. Yeah. Okay. Yeah. Thank you.